All right, now we're going to move on to another instance of the use of the t-test. Instead of having one group that's measured twice, what we're going to have is two independent groups, two separate groups that are each measured once. So the t-test before referred to as dependent means t-test because they were correlated. They were the same subjects sampled twice, often at 2 points in time, or two different measurements that are compared. Now here we've got two different groups that constitute the two measurement times, the two means we're going to compare. And that's why they're referred to as independent. These are separate groups, not the same group. Dependent means t-test was the same group tested twice. Here we have two separate means from two separate groups, and that's referred to as independent. So there are numerous examples of this. This is probably the most common application of the t-test, is to compare two groups, males versus females, young and old, any kind of contrast that involves the grouping two groups, an experimental group and a control group, things like that, all involve the application of the independent means t-test. And when you do this kind of t-test, the dependent measure, the thing you're comparing, must be the same for both groups. So you have to use the same test or the same measurement of outcome from a study, and so on. They have to be the same measurement from two different groups of people. And then you're going to compare those two means to find out if they're significantly different. Here's a schematic of the independent samples, the independent means t-test, where there are two different groups compared. And so you have two populations, and we'll say this is males and females. So you have two populations. Now within these two populations, you're going to derive distribution of means of samples. Remember the exercise where we derived the distribution of means of samples taken from populations. So you have those two just like before. And now you're going to compose a new comparison distribution that represents the distribution of differences between the means. So if you were to subtract the two means that are being created above in the second level there, you would end up with a distribution of difference scores, of differences between means, and that then becomes the probability distribution you're going to use to make your inference. Okay, so you've got samples of a certain size. You create a distribution of means from the populations by taking samples of that size, calculating the mean, and then creating the distribution at the second tier. And now you're going to subtract the samples that you've created, or subtract the means. When you do that, you get a new distribution that represents the difference scores, the distribution of differences between the means. Because what you're going to be doing, is making an inference, are these two means different? And so you need to know what the normal distribution is for differences like that. And that becomes the probability distribution you use to make your inference, to formulate your cutoff, get your area under the curve, and everything. It's just that now the comparison distribution is going to be this difference score and not the distribution of sample means. Now we're going to go through the steps of hypothesis testing for independent means t-tests. This is basically the same set of hypothesis testing steps that we did before, just that now we're going to apply them to this new variation on the t-test. Okay, well, step one always involves the same issue. Restate the research question. And here we've got an example where we're going to figure out if men tap faster than women. It just is an example exercise. So you want to restate the research question, and you want to state a research and a null hypothesis, and you want to refer to populations. Okay, so the research question is, do men tap faster than women? The research hypothesis is going to be restated as the population mean, a tapping score for men, will be greater than the population mean tapping score for women. The null hypothesis is the two population means are the same, just like before. Except now we're referring to two separate groups, men versus women. We're going to have two separate samples of men and women. Whereas before we had two means, but they were for scores taken on the same sample at 2 points in time. Step 2 of hypothesis testing is to determine the comparison distribution. And this is the distribution that you're going to use to derive your probabilities, that your result could have occurred by chance or not. Now, for an independent means hypothesis test or independent means t-test, your comparison distribution is not a distribution of means only. It's now a distribution of the difference between the two means for the two separate samples. It's like you're going to get estimates of population parameters from each sample, so you need to have a comparison distribution that incorporates the variability and the error that's in two samples now instead of just one. Now, if the if you do have now a difference between two means, then the mean of that distribution is going to be 0. So if you actually had, imagine you had subtractions and all the means were the same, they would actually cancel out to 0. The comparison distribution of differences between two means, because it's a subtraction, is going to have a mean of 0. Now there's going to be scores above and below that. So when you subtract two means, some of them will be positive scores, some of them will be negative. A majority of them will be very close to 0. They'll be very similar. And so the mean of that distribution will be 0. The population variances you're going to estimate from the samples are assumed to be the same. There's an assumption that the population variances for the two populations, in this case it's men and women, will be the same. We won't have some sort of skewness and some kind of odd variance in the distribution of these two samples in these two populations. And the variance is estimated from the average variance that's in both samples. And this is referred to as the pooled estimate of the population variance. You're going to be estimating variance from two samples. You have to combine them somehow. And you do that with a formula for estimating the pooled variance. And if you have unequal sample sizes, which you could easily have in a real study, then the pooled estimate has to be weighted by the numbers in each sample. So you don't want a sample of say, a small number to have the same influence on the population variance estimate as a sample that has larger sample size. And so you weight it based on that. And you'll see when we do the formula later how this weighting is done. Basically what this slide is about is showing you how the population variances are estimated from sample variances when you actually have two populations. See, up till now we've not had two populations, we've only had one. And we've either known the population parameters, so we don't need to estimate from samples, or when we did the dependent measures t-test before, we have only one population, even though we've taken scores from two different points in time with that population. Here we have two different populations, so we have to have a formula for combining our estimates. Okay, here's how we calculate the pooled variance estimate of the population variance. It's part of determining the comparison distribution, step 2 of hypothesis testing. If your samples have unequal sample size, then the pooled estimate must be weighted by the numbers in each sample. So you take the degrees of freedom for estimated variance, which is n minus 1, and you take the degrees of freedom for variance of the means, which is n, and your total degrees of freedom is equal to the sample 1 degrees of freedom plus the sample 2 degrees of freedom. So there's the formula down there at the bottom. You take the sample 1 degrees of freedom divided by the total degrees of freedom times the variance of sample 1 plus sample 2 degrees of freedom divided by the total degrees of freedom times the variance of sample 2. And that's how you actually calculate the pooled estimate of population variance. Now you can see this is a variation of the equation we learned before for estimating the population variance. It's just that now we've got two samples. So we have to add in the influence of each sample. Then you need to weight this for sample size so that each subject, in a sense, has equal influence on the population estimate. And so imagine if you had sample size, say 20 males in this study and 50 females. If you average the variance of the samples, then the smaller sample of males would have a bigger influence on the population variance estimate than it should. Then if you pooled them in some way and then weighted the estimate based upon how many subjects you actually have in each sample. In other words, if you had a sample size difference like that, the men would have as equal influence as the women, even though there's so many more women. They ought to the sample size ought to be weighted so that each subject contributes equally to the estimate of the population parameters. Okay, the next step is to figure the variance estimate for the distribution of means, for each distribution of means. If you remember back in the graph before, there were two distributions of means, one corresponding to each sample. Okay, the formula for this is down below. The variance of means for population 1 is equal to the pooled variance estimate divided by the number, the n, the sample size of sample 1. And the variance of means for population 2 is estimated to be the pooled variance estimate divided by the sample size for sample 2. Now you can see this is very similar to what we did before. It's just that now we've got two samples again. So we have to make two variance estimates for the comparison distribution of means for each one of these populations in each one of these samples. So we're going to do one for men and one for women, and this is the formula to do that. You can see where it's based upon the pooled variance estimate. It's assumed that the two populations have the same variance, and so you see that the pooled variance estimate is used for both of these. It's not a separate one for each one. And you divide that by the number in the sample, and that gives you an estimate of the variance of means, population 1, and the variance estimate for population 2. Okay, remember now the comparison distribution for the independent t-test, independent samples t-test, is going to be a difference between means distribution. So now we have to estimate the variance of the difference between means so that we can calculate eventually our probabilities and everything. We're all gearing eventually for the testing hypotheses by using this distribution to estimate probabilities of a difference score between our two means. And so we need to know what the variance is for this comparison distribution of difference scores between means. Now to calculate that, it's relatively simple. You take the variance of population 1 distribution of means, which we just calculated in the previous slide, plus the variance of the population 2 distribution of means. You add those two together, you get the variance estimate for the difference between means. All right, step 3 of hypothesis testing is to determine the cutoff for a significant result. And just like before, we pick usually conventional values of 0.05 or 0.01. And you look up in a table, usually for t in the back of a textbook somewhere, the cutoff values for t-scores that correspond to p probability less than 0.05 or probability p less than 0.01. And of course you've got to portion this for one or two tail tests, just like before when we did the z-distribution. It's just that now the t-distribution, since it's estimated from samples, is going to have a slightly more conservative in the tails, so the cutoff values will look different in a t-distribution than they do in a z-distribution. And that's really the only difference. And again, as the sample sizes get really, really large, these numbers actually converge, and so the t-distribution starts to look a lot like a z-distribution. And that's because with a large, very, very large sample, you can estimate the population parameters with very great accuracy. So it's a lot like having actual knowledge of the parameter rather than estimating it. And you're not really estimating it anymore because now your samples is so large, it's as if you've reached the size of the population itself. Okay, step 4 is to determine the t-score for your study. So now that you've got your criteria established for probability and you've got your t-distribution all set up, now you want to calculate your own t-score and then compare this to the distribution to see if your result likely could have occurred by chance or not. Okay, so the degrees of freedom for the t-distribution is the total degrees of freedom. The t-score is equal to mean 1 minus mean 2 divided by the standard deviation of the distribution of the difference scores, or the differences between means. Okay, let's look at this for a second. Here you see mean 1 minus mean 2. Now our hypothesis said that men will do better than women, so you'd expect the means to be different. So mean 1 tapping score will be different than the mean 2's tapping score, and that's what that first subtraction tells you, is how far apart the two means are. And then you divide that by the standard deviation of the distribution of the difference scores. Okay, so think about that for again. This is the distribution of differences between the means. So you've got a mean difference here. You've got mean 1 minus mean 2. And now you want to calibrate that by the variance that's in the distribution of mean differences. And that's how you calculate t. And we'll, in the next step, in the next slide, we will calculate this in more detail. Now we want to compare our t-score to a cutoff score corresponding to a probability level and make our decision. Now this is what a typical t-test looks like, a t-test table looks like in your textbook. Notice here we've got two sets of columns, one for one-tailed tests, one for two-tailed tests. We have them arrayed by degrees of freedom. And degrees of freedom is a facsimile of sample size. And notice under each one of them we have three probability levels, 0.10, 0.05, and 0.01. Here in this graphic they're depicting the 0.05 level is the one chosen for a study. We have degrees of freedom of 15, and you go across that row, and it's telling you in that row what t-scores you need or higher to meet that criterion level for that probability. So at 0.05 level, we need a t-score with 15 degrees of freedom. We need a t-score of 1.753 or higher to make an inference that our result did not occur by chance. The mean difference divided by the standard deviation of the population of mean differences is equal to that number or higher, then that mean difference likely did not occur by chance. Now we're going to have an example of how you calculate the independent samples t-test. Here we have an example problem with data, and we've been discussing this as an example theoretically, and now we're actually going to do some data analysis with SPSS. Okay, so our research question is, do men and women differ in fine motor speed? And we went through the steps of hypothesis testing. So we define our research hypothesis to be that the two population means will be different. Our null hypothesis is that they're going to be the same. Okay, here we've got men and women. You go out and actually collect your data now. You've got to go out and do a study to test this hypothesis with empirical data. So you go out and you get a sample of men and a sample of women. You ask them to tap on the space bar of the keyboard as quickly as possible in 10 seconds. And that's your dependent measure. That's the mean value on that is what you're going to compare to do your t-test. Okay, the table at the right depicts this data. It shows you this data. So here we have the gender, 1 for male, 2 for female, and the number of taps that each subject did. So they were asked to tap on the keyboard as fast as they can in 10 seconds, and these are the values that were rendered from that test, from that analysis. Okay, you can download this data at the course website. There should be a link there. The file is called gendertap.sav. It's an SPSS SAV file. The link, though, is called something like gender and tapping, something like that. You should be able to see it pretty easily if you go to the unit and download the file. Then run SPSS, open up SPSS on your computer, and open up that data set. And hopefully you can run this again or run them both in 2 different windows on your computer so you can see what the data analysis is from SPSS, as well as continue with this presentation. When you go to SPSS, go to the Analyze menu of SPSS and choose Compare Means under that menu. Then choose Independent Samples t-tests. It'll start running. This is after you've opened up the data and the data has been entered in SPSS, just like you've done before with the homeworks. You should then get a dialog box that comes up and asks you about what variables you want to analyze, and indicate that the variable called tapping is the test variable, and gender is the grouping variable. Now the next thing you've got to do is define the group codes. So you have to click on a little button there at the bottom right called Define Groups, and you enter a 1 for male, 2 for female, and that way you're telling SPSS how you're coding the grouping variable. Then click OK. After you click OK, SPSS should run the analysis, and you should be able to look through it, see the means and standard deviations of the samples. You're going to see some things there you don't understand, but right now just look for the t-score. There's a column there for the t-score. And it will give you a p-value, a significance level associated with that t-score. It's the actual probability of that t-score. If that significance level is 0.05 or smaller, then you've met the criterion for the t-score probability level. Now in this examples and in your textbook, you look things up in a table in your textbook. But of course SPSS has the capacity to actually calculate a probability and just give you the probability that your result could have occurred by chance. And if it's 0.05 or smaller, that means that it's very unlikely that it occurred by chance. It's something that by design, something that's actually in the environment is a difference. And I think I designed this so that there is a difference. So the t-value ought to be high enough to indicate that one group is different than the other. I don't remember if the males tapping faster than the females. I think it is, but you can check that for yourself. Every statistical test has some assumptions, and that's because when you're calculating probabilities from a distribution like this, from a bell curve, from a t-distribution, there's assumptions about the variability that's in the samples and in the populations, because they've got to match the contrast you're making to calculate probability, so they have to match the underlying assumptions of that curve. What are the assumptions of the t-test? First is the distribution of individuals must follow a normal curve. So the population has to be normally distributed. If there's significant skew in the population, then you can't use a bilateral distribution like this, a t-distribution, to make your probability judgments. They're all going to be off by some degree, represented by the skewness that's in the population. And you could go through and create different t-distributions for different types of skewed distributions. But of course that would just be totally unwieldy. And so there's an assumption that the distribution of the populations has a normal curve. Now, a number of studies have been done comparing t-tests under different conditions of skewness, and it's been shown that the inference you make is actually quite robust. The distributions of populations have to be quite skewed before the t-test becomes invalid. The next assumption, 2 populations have to have the same variance. So you can't have a population that's real narrow, and if it has very little variance, you can contrast it with another population that's got a lot of variance. The 2 populations have to have roughly the same variance. Again, this has been studied by statisticians, and the t-test is very robust for a violation of this assumption. And so if one of the distributions is, has half the variance of another one, you can probably still use a t-test, and you probably still should, because the inference you make, even though the t-score might be slightly off, the inference that you make about the 0.05 probability and all that will still be quite valid, even if the samples and the populations have pretty large differences in their variance. But again, since the probability judgments are based upon a certain model for a curve, you've got to have that curve in your data. And if you violate that assumption, what you need to do is, what you would do in that situation is go to test statistical procedures that don't have these assumptions. And we'll get to those at a certain part of the course. But that's what you do. So if your assumptions are violated to a significant degree, you transition from a t-test into another kind of statistical procedure that doesn't rely on that assumption. Now we're going to calculate the effect size for our example, for our t-test for independent means. Remember, effect size is a way of calibrating how far apart the means are. It's a way of, even if you have a lot of significant results, sometimes they're not very big. Even though they beat chance, they're not necessarily very large differences. And this is a way of calibrating how large a difference you found between the two means. Basically, it's a ratio of the mean difference to the variance in the different scores. So D is equal to population 1 mean minus population 2 mean, divided by the standard deviation of the different scores. Because see, now we're subtracting two means. So the variability is going to refer to the variability of the distribution of different scores. And now SPSS gives this a name. It's called if you go to the SPSS printout, you'll see where the T, and next to it is the significance level. Then it shows the mean difference. It shows the average mean difference. And then it shows you the standard error of the difference score. Now the standard error of the difference score is the standard deviation and the variability of the difference distribution. So you have a mean distribution. A mean of that distribution is 4.89, and the variance of that distribution is 1.48. So that's what we plug in here for our effect size. And so when we subtract the two means, we get 4.89 divided by 1.48. It gives us an effect size of 3.30. Now that's a large effect size, I would imagine, although it's not. It depends on how you conceptualize your study and the dependent measure to sort of determine how large that is. It also suggests with a variance like that, the variability in the samples is quite small. If we go back and look at that in SPSS, if you go to the first table that it shows you, it gives you the mean for each group. In this case, we've got men and women. The mean tapping score is 49.75. The standard deviation, though, which is the measure of the variance, is only 2.31. And that's, we got a mean of 49 and a standard deviation of 2.3. That means that distribution is very narrow. Also, the distribution for women is narrow. Their average is 44.85, but again, their standard deviation is only 3.38. So this indicates that even though the variances might be equal, maintain the assumptions of the t-test, there's not a lot of variability in the sample. And so the variance estimates are reflecting that. Anyway, our effect size here is calibrated by the mean difference divided by the variabilities in the different scores, variabilities within the populations. And we discovered that it's still quite large. Power in the t-test for independent means. Now remember, power is the probability of finding a significant result when it's actually there. Finding a significant result with your study, the way it's designed, when it's actually in place, when it really exists. And here this table shows you the relationship of sample sizes to effect sizes. And it's similar to what tables like this we've seen before. First of all, you need to calculate the harmonic mean if you have unequal n's. And that makes the sample sizes equivalent and treats the power calculations as if the samples were equal. This table down below shows you the relationship between power, which are the numbers here as decimals, The sample sizes are on the left, and then across the top you see the different effect sizes. Now as you go down this table, you see where there's the sample size increases from 10 to 20 to 30 and so on. As the sample size increases, the probability of finding an effect increases, and you can see where it increases dramatically if it's a medium or large effect size. So for a large effect size, which is a D here of 0.8, you only need a sample size of about 20 to meet a reasonable power expectation of 0.8. And by convention, 0.8 is usually chosen as a reasonable power expectation. But now when you go to the medium effect size in the middle, you need a sample size of approximately 50 to reach 0.8. And then for a small effect, you don't reach it even with a sample size of 100. Now this is clearly depicting that the probability of finding a significant effect when it's actually there varies with the sample size you pick and the magnitude of the effect size. It's easier to find large effects, and that makes sense. A large effect is a big difference. You don't need many subjects to show that. A small effect, though, is hard to find. You need lots of subjects to show a small effect. And that's the relationship between power and sample size and effect size. This table turns the power calculation around a little bit to where you can use power calculations to actually plan your studies. Now this is a very potent use of power calculations now, and it's when people are proposing research grants to the government and things like that. The government agencies expect you to estimate how many subjects you'll need for your study because that influences how much money you'll need to conduct the study. So what people do is they set power at some reasonable level like 0.8. They choose a p level of say 0.05, a conventional level. They assume equal sample sizes, and they're going to do a t-test. Now down here you see the sample size to detect small, medium, and large effect sizes. Now so a large effect, and it also shows you the relationship between one and two-tailed tests in this. To detect a large effect, D equals 0.8, given these conditions, you only need a sample size of 20 or so. To detect a medium effect, you need a sample of around 50. To detect a small effect, which it is, you need 310 subjects for a one-tailed test. So you need lots of subjects to detect small effects, and far fewer subjects to detect larger effects. You can see where it's exponential. Now, most researchers will propose a medium effect size, although I think most researchers believe their effects are quite large. They really expect things, if they have a new drug treatment or something like that, they really expect it to cure people, to have a big effect. Yet when they're proposing a grant, they'll be much more modest, and they'll say, well, it should affect, half the subjects or so at a certain level, and they'll propose a medium effect size just because they don't know the outcome of their study. They don't want to propose a large effect and only get enough money to study 20 subjects, and so they propose something medium, anticipating enough money to detect a medium effect size. And sometimes drug companies will actually go out there and choose sample sizes that are extremely large, trying to find a small effect, because until recently the FDA only required them to have statistical significance. They didn't actually have to find a medium or large effect for their drug. So if they found a small effect, they could get their drug out there for sale. And it wasn't uncommon for drug companies to go out and collect sample sizes of thousands and thousands of subjects, anticipating that they'll find something. And once they find something, some significant result, they can go out and start selling the drug, even though it actually might have a very small effect on the disease. At any rate, this table shows you what kind of sample sizes you need to find different kinds of effects given a power level of 0.8. The problem of too many t-tests. Well, in this era of modern computers, it's so easy to do statistics that once you have a data set, you can generate all sorts of contrast between two groups and generate sometimes up to thousands of t-tests. Well, if you choose a p-level of 0.05, then that means 5% of these t-tests will come up significant just by chance. So you got a problem there. If 5% of these are coming up just by chance, that means if I do the studies again, another set of 5% will come up by chance again. And I'll end up with this quandary of interpreting insignificant t-tests that only occurred just by chance variation in the study. Another manifestation of this is when you have dependent variable sets in your studies that are not really independent. And if they're correlated, then you'll come up with lots and lots of significant t-tests, not because you're measuring something independent, but because they're all the same thing, and you come up with significance on these dependent measures. And it appears as if they're independent measures. They're all measuring something different, and so you have this quandary of all these t-tests you got to interpret that came up significant when they're actually measuring the same construct. Well, when you have a situation like this, researchers through the years have advocated controlling the p-value as a way of correcting for this. Unfortunately, what happens in thousands of t-tests, though, the correction of the p-value is so great, nothing comes up significant, and you have a problem in the opposite direction, where you should have something significant. Probably some of these are significant. They didn't occur by chance, and they should be interpreted. Because your p-value is now so conservative, you don't interpret any of them. And so if a t-test can only be significant at the 0.00001 level instead of 0.05, very few of the t-scores will come up as significant. This problem has not been resolved. I think the situation now is people will try to correct it with p-value corrections. There's a thing called the Bonferroni correction, which basically just simply divides the p-value by the number of tests that you made. The problem is still here, though, and the problem is really expressed by the recent practice of analyzing the data with so many t-tests that a number of them come up by chance. And it hasn't been really resolved what to do about this. Probably the way to resolve this has to do with a theoretical model of what you're studying and how carefully you've thought that through. If you're just out there collecting lots and lots of data, and now these days, you can just collect thousands and thousands of variables on people without having any theory about what is related to what kind of discriminations will be made, trusts are valid. You're just out there in a kind of a fishing expedition, just finding out what might be significant, say, between men and women. You'll come up with chance findings. And unless you start out with a very clear theoretical idea that establishes what your hypotheses are, you can sit there with spurious, completely chance findings, discussing them all day, and when it comes down to it, what's happened is just a flip of the coin has produced a chance result, and you're going to town all these things that it means. What you need to do at the front end is make sure that you refine your dependent measure set to a set of hypotheses, that you have a strong theoretical model that will explain differences if you find them. If you don't have this theoretical model, you'll go out there and collect lots and lots of data, crunch it all down with t-tests, and you'll end up with 5% of them or so discovered by chance. You'll start to try to interpret them, but you really shouldn't. You really should, a priori, at the front end, be able to make an interpretation rather than trying to do it at the back end, just because you get a statistically significant result. The other way to interpret that is if you only get 5% of your t-test significant on these kind of fishing expeditions where you don't really have a good theoretical model, then interpret those as likely to have occurred by chance and don't try to make sense out of them. The admonition is really to have a strong theoretical model before you do any study. That will tend to reduce the number of t-tests you do because it will tend to reduce the number of dependent measures in the study. And once you do that, you're well on your way to figuring out just which t-tests you should examine to test your theory, and not just go on a fishing expedition, find differences, and then try to make sense of them later. Finally, for this section, why don't we do another example using SPSS. There's a data set at the course website called Gender and Salary, or Salary Data, something like that. There's a link there. When you click on it, it downloads a file called salary.sav. Now, this data set was collected from a company that was being investigated for discrimination in salaries. And so it's a large data set with all the employees and what their salary levels are, their gender, their education, their seniority, all kinds of things are in the file. There is a variable called current salary, and of course there's a variable called gender. So do another independent means t-test in which you compare men and women on their salary levels. And feel free to compare anything else in the data set you might want to try to compare. There are things like there's beginning salary, there's seniority, there's all kinds of things you might want to investigate. And plus there's other variables that might be dichotomized like gender that you could compare with dependent measures like salary and things like that. So give that a try. Download the file. It's an SAV SPSS file. So you have to double click on it. You'll see all the variables in there. Go to the Analyze menu, choose Independent Means t-tests, and so on, just like we did before, and do a t-test comparing men and women on their salaries.